Hello and welcome back to today's webinar on condenser performance, essential monitoring, air-in leakage evaluation and reporting with Dr. Tim Harpster of InTech. I'm Kathy Regan, the editor of Energy Tech Magazine, and I will again be your moderator today. With that, I will turn things over to Dr. Harpster and we'll get started.
Hello, thanks for joining us again today, everyone. This will be the second session, so let's get started. Yesterday I covered the essentials for performance monitoring, the instruments that are used for that, the formula and validation of the standard parameters. For example, we covered the importance of the proper location of pressure taps, making sure they're down near the bundle, not up near the turbine. Using pressures and temperatures to validate the condenser pressure measurement. So one that we showed yesterday was using the hot well temperature or exhaust pressures or some other pressures and temperatures that you might be measuring on the condenser to validate the pressure that you're using for performance calculation. We covered important techniques like using a no load time period to validate cooling water temperature instruments, those values. The importance of proper location for those measurement points as well. And I showed a cost-effective way to, well, what I believe is a cost-effective way to continuously measure cooling water flow. It's a parameter that's not often monitored. And so if you ever need any help validating data, evaluating your models, making sure they're using the latest and greatest formulas. We talked about HEI has evolved over the years. But if you ever need any help, that or maybe even adding some test grade condenser measurements to your re-evac monitor, then please, give Jason, Colin, myself a call, and I know we can help. So today I plan to use data and the model calculations to troubleshoot real problems. Yesterday, I asked the participants to tell us what problems they're having, and we got some responses back. So let me share some of those with you. Some of the responses I got were one individual is having problems of D-rates in the summertime. It seems like a really important problem they're having. Several people got back to us and they said that they have been battling high air-in leakage from various different sources or unknown sources. Another person got back to us. They said that they're performing engineering evaluation in response to a dramatic increase in their cooling water inlet temperatures. So something environmental or configuration of the configuration of their system or their cooling water source has changed. And now they're getting cooling water inlet temperatures that are much higher than the plant originally had, apparently. So, these are all some of the issues that your peers that are in the class experiencing. And so my hope today is that after completing this session, you'll have developed techniques to more rapidly quantify and resolve some of these issues, some of the air and leakage, vacuum equipment, and fouling related issues. Now this slide was shown yesterday. Oh, I wanted to go back. So for each of the case studies, I'm going to try and hit these topics as it's outlined in the class. We'll first, we may quantify the benefit. What is the value in going after this case study? What is the problem? What is the value there? We may handle that first or last for some of the case studies, but then we'll make some observations on the data, which I will be asking you to comment on. So, when I first put up those data slides, I'll be asking questions at the end of that slide. I've provided a handout. Typically, when we do this class in our own workshops, we have those handouts printed out for all of the attendees. It might be useful for you to print out the data handouts, print those out so that you can have my slide up on the screen and be looking at the data on the side. You don't have to do that. It's just it's a good way to do it. And so those slides are all labeled. So I'll try and reference those as we go along. But I'll be asking you for your thoughts on the data. So then we'll, in some of the cases, not all of them, we'll do some data validation. I'll show you some techniques That gets a little bit tedious after a while, so I'll stop doing that for some of the case studies, but there's some good good techniques in data validation that's always important to validate the data you're looking at first before making any conclusions. So data interpretation, we talked about that, and then finally solving the problem. Okay, so this slide was shown yesterday. It's from EPRI's heat rate improvement manual. It lists the rule of thumb here for the heat rate impact per inch of mercury, back pressure, industry utility average. That looks a little bit high to me, but maybe it's an average. So anyway, and it lists the causes for excess back pressure. And on this list, you'll see some of the usual maintenance-related issues that you're facing that we just talked about: air and leakage, fouling, things like that. And so, figuring out which one of these is causing the biggest problem quickly and reliably is going to be a focus for these case studies. So, very quickly figuring out, is this an air and leakage problem or is this a fouling problem, will be a focus. I do want to make sure that we all understand that what's not listed on this list, which I'm sure all of you are very aware of, is that air and leakage and vacuum equipment capacity, they're two separate things, but they're very much related. It's like two issues, two sides of the same coin, really. You can have high air and leakage and excess back pressure, or you could have low air and leakage but low vacuum equipment capacity and have high condenser pressure. So it's important to just recognize that figuring out which one of these is the issue is also important. So I have this slide here. You can't read anything on it, I know, but I've chosen this slide as an example of a document that has a compilation of causes for a high condenser pressure and effective detection activity. And so I'm going to zoom in. I don't know if you can see this, but this is a fishbone diagram. The effect is high condenser back pressure. You might be able to read it right there. And then on these bones, these stems, there's all these different potential causes for the high excess back pressure. And what this document has, what this customer is actually doing, is listing not only the specific piece of equipment, but also a method for checking that piece of equipment for that particular cause. And I really like this document because it can be very helpful to streamline your efforts for solving a problem. You don't necessarily have to have this fishbone diagram, but it's a nice single document that can be passed on to new engineers, a consultant service, or even you can use it as a to-do checklist. You check off each one of these. I've checked all of these things to try and track down this high back pressure, but it's got the fundamentals of what you would need to do a complete assessment of the high condenser pressure. It's a nice single document that has the cause and effective detection activity. So I wanted to show that. Now this slide is an example of flowcharts that exist to help you take very specific step-by-step actions to troubleshoot equipment. And so let's zoom in on some of this here. Here's one up here. Is the vacuum equipment leaking? And so there's some very specific steps and decision trees to go through to figure out if the vacuum equipment is leaking. There's a whole bunch of steps to figure out if your exhauster capacity has at an expected flow rate. And I'm not going to go into all these in this session. Okay, these are very specific equipment troubleshooting steps. The important thing on this slide is I've listed some references for you. This presentation is going to be a much higher level focus than these very specific troubleshooting actions. But I've listed these references that have useful flowcharts. They have useful tables. Some of them have case studies that are excellent resources for troubleshooting and fixing problems. So the references in this whole presentation, this whole class, are intended to be good resources for you. And so that leads me to my first question for today. I'd like to ask, for the benefit of all of the attendees, if you have a document, if you have a reference, maybe it's a flow chart, or maybe it's just a really long, complete document that you use for your troubleshooting efforts that you've found useful in the past, submit that to us in the question box, and we'll be sure to forward that out to the other attendees. Let's share your experience, your best references with the other attendees in the class, and I'll make sure that those get out to everyone. So if you can, if you have some, that you've used before, just go ahead and type it into the question box. I'll compile it at the end of the class and make sure we get those out to the attendees. I'm not going to wait for that. I'm going to continue on, but if you think of one as we go through the presentation, please be sure to share it with the other attendees. So that leads me to our first case study. Let's dive right in. So this case study is a 325 nameplate megawatt power station unit. They have a Westinghouse starburst bundle arrangement condenser. We showed that yesterday. It's not a very good condenser. They have some issues with that. They have very large Nash 3004 pump vacuum pumps. These are the big daddies in the industry. Those are very large pumps, and they have typical instrumentation issues that are listed here. Some of the issues that we talked about yesterday, and they have many years. The engineer there has many years experience of combating high condenser pressure, and so that particular engineer hired Intech and several other consultants to do reviews of the system and make recommendations. And so that's where we entered the picture for this case study. So I'm going to walk you through some of the process, some of the actions that plant took, and some of the issues that we found. So I want to focus in, first of all, let's value the problem at this plant, okay? 3 to 6/10 excess back pressure at 200 megawatts, that's the reduced load, that's where they idle. And then 1/2 inch to 1.2 inches historically at their max load 325. So let's just try and value that. I've put together this slide. You can do this calculation. I should probably send out this Excel sheet. It's a really simple Excel sheet. But I understand you guys have probably much more sophisticated algorithms for valuing excess condenser pressure. So I'm not going to focus too much on the accuracy or application of these numbers for your plant, but just let's get the method down, use what we learned yesterday to put some value to that excess back pressure. Now this is a cost that we did not talk about in the past, but if you run a backup pump to say try and reduce condenser pressure, there's a lot of plants out there that will run their backup pumps all the time, no matter what. Some of them turn it on if they think they have a problem, but there's a cost to running that pump, and so that cost is estimated here. We're just using the horsepower of the pump, the capacity factor. The unit doesn't run all year long, so we got a capacity factor there, pump motor efficiency, and the cost of power, which may not apply to you, but I've used 7 cents per kilowatt hour here. So anyway, this for this particular Nash 3004, if they're running that extra vacuum pump, it's 60 grand a year, so 5,000 a month to run that pump. So that's one cost here. Over on the right is the cost of the excess back pressure. So this plant cycles. It's high during the day, low at night, like most of you probably are. So there's their 2 generation loads. I've used, if you recall, the heat rate correction curves that we used yesterday. This percent heat rate per 1 inch mercury is derived from that sheet. So you'd have to go back to that plot and grab these numbers for your analysis so that it's specific to your plant. But that's where this percent heat rate comes from, is from those correction curves. And then the capacity factor at the load, you know, you're not at high load all the time. This particular plant's there about 40% of the time, low load 40% of the time. Again, another custom parameter is the heat rate at that load. You know, I've used I think a fairly conservative heat rate of 7,000 BTUs per kilowatt hour at the high load and 9,000 at low load, because it's not, your plant doesn't run as efficiently at lower load. And then there's the excess back pressure for this particular case study, 5/10 and 3/10, again, pretty conservative numbers based on what I just showed. And then the price of power, what can you sell that power at? Again, 7 cents per kilowatt hour. The cost of fuel is in here. Again, this is another number that would change from plant to plant, but nonetheless, that's there. And so there's two different ways to value this excess back pressure. The one is if you are losing ability to sell megawatts. That's a heat input limited condition. We talked about that yesterday. So the value of this back pressure at these loads would be $800,000 a year. But most plants don't do that. It's really fuel cost savings is how you would value this excess back pressure. We talked about that yesterday. And so if you're calculating the excess fuel cost, that's quite a bit lower, about $300,000 a year for this particular case study. So this problem at this plant, very conservatively is about $28,000, or less conservatively about $71,000 per month for whatever problems ail this plant. It could be a multiple problems. So anyway, as I mentioned, you know, this condenser, this unit has a Westinghouse. Part of the problem is definitely the condenser configuration. And they've got other issues as well. As part of a basic analysis effort, we found issues with their instrumentation, and so a basic instrumentation package was implemented and installed, and that's listed here. I'm not going to go through each of these. I'd rather describe it in an image, but you have this slide if you want more details about what they installed. I'm going to skip to the image here. They installed re-evac equipment on their air offtakes or non-condensable offtakes here, 2 of them, 1 for each side of the condenser. They have circ water flow DP instruments, you know, on each water box, and now they have the flow rate through each path of the condenser. So the cooling water flow rate through here and the cooling water flow rate through there. Some pressure, test grade pressure and temperature measurements. We went through the CFD analysis and figured out where to put temperatures on there, and so they have probably more than what you would have at your facilities, but this is the instrumentation that we have on this for this particular case study. By the way, this whole case study you can read about. It's published actually through Energy Tech. Well, that link's not going to work for you guys, but there's the title. You can just Google it, and so we're going to talk about that case study. The unit has a main, basically a main computer that brings everything in. It's a standalone unit, but the unit can also send the data to your data archiving unit. This is what it looks like at this particular facility. It's just a simple wall unit here. It stores all of the data locally and it has a user interface. So as part of the case study, let's take a look and see what the plant engineer has access to. So here's a somewhat decent screenshot of the unit. You can see here that we've got, with that instrumentation installed, we've got flow rate per path. So you can see 76,000 gallons per minute through each path of the condenser. The total flow rate shown there. The cleanliness factor, performance factor is being calculated with all of this information. We've got the flow rate, the inlet, the outlet, temperature, so we can calculate duty and the cleanliness factor there. We've got the condenser pressures, 2 of them, 1 at the hot and cold end. We've got circulating water temperatures, inlet, and then 4 on the outlet here. That fairly decent spread in the data for the outlet temperature that we've located as far downstream as possible. And we have re-evac measuring air and leakage, pump capacity, and some other values that we'll talk about. So this instrumentation was installed in 2015, and in 2015, when the unit came on, the unit's giving its first data to the plant engineer. Let's take a look and see what we found. So I only have a few of the data points plotted here, but the important ones for this case study. And so let me describe what they are, and then we'll talk about what we should expect to see from these values. And then I'm going to ask you all what you think, what you observe, what is the problem that you observe, and we'll try and troubleshoot this problem. So the green line here is the total flow rate through both paths. So the total cooling water flow rate here. The red line is the calculated cleanliness or performance factor for the unit. As I said, this unit has a host of issues. You know, it looks like it came up here with about a 67% cleanliness factor. That's about as good as this unit does with all the issues it does have. So just to give you a baseline for that. And then here in the dark blue and light blue is the cooling water flow rate per path. As you saw in the image of this plant, there's two inlet water boxes. And so there's the cooling water flow rate of the blue, dark blue is the west side path, and the light blue is the east side path. And so this unit comes up with one circulator. This unit's coming out of an allege. They were still performing maintenance on one of the two circulating water pumps, so only one circulator was initially available. Okay, and then at this point you can see they turned on the second circulator. So as I mentioned, the cleanliness factor shown in red is started at 70%, and so I'd like to start to ask, what do you guys see in this data? And go ahead and respond in the question box, okay? When this unit comes on, I think you guys would all think that you would expect to see the performance factor come up and stay flat. I think you would expect to see the cooling water to come up with one pump and stay flat, and when the second pump comes on, go up and stay flat. I think you would also expect that the cooling water flow rate per path, when you turn on one circulator, should come up to, you know, a one circulator flow rate and stay flat. And same with the east and west path, they should come up and stay flat. Yeah, so it looks like we've got an answer here. So yeah, that's okay. They're flowing in now. So yeah, it looks like we have a cooling water issue. So what's the issue? Okay, what's happening in here is let's take a look at the west path, just the red line here. So the cooling water comes up to a value and it starts decreasing. Cooling water is decreasing. And so at the same time, we're seeing the east path increasing by almost the same value. It's as if the flow rate is shifting from west to east. Okay, and then in the total flow rate, you can see that in the green line, it's just constantly decreasing. The one circulator comes on, it constantly decreases. And then when they turn on that second circulator, it's continuing to decrease. Okay, this is what happens when you get preferential debris fouling. Okay, so what happens typically when you get debris fouling, so something, this is fouling that gets into the cooling water and blocks up tubes. What happens is that debris typically follows only one path of the cooling water. The debris wants to stay straight in the cooling water pipe, so it tends to go to the very last water box in the cooling water chain. And so the west box is actually the furthest from the cooling towers at this plant. And so that debris it continues on straight, and then it takes that elbow up and turns into the water box and goes into the condenser, and it preferentially fouls the west path. And so when that starts blocking up the cooling water going into the west path, the flow rate through the west path decreases. Well, the pumps are still trying to deliver the total cooling water flow rate, but it can't push that flow rate through the west path, so the east path flow rate goes up. The reason for the total flow rate decrease is because of this obstruction, there is now additional head pressure on the pumps. And so the total flow rate that can be delivered from the pumps is affected by that head pressure on the pumps. And so the total flow rate decreases due to this plug-in. Okay, so let's take a look at an image of, before I get to that. Yeah, go ahead.
There was another question. Is the cleanliness factor based on 100% as stated yesterday?
No, it's just straight out of the HEI values. So it is not based on 100%. It is just using the formula to calculate the measured heat transfer coefficient over the ideal HEI heat transfer coefficient. That's really what cleanliness factor is. It's your measured heat transfer coefficient divided by the model, good flow rate, good inlet temperature, good tube material, good clean tube, divided by that determined heat transfer coefficient. So it has nothing to do with, like a random factor. It's just straight out of the formulas that I showed yesterday. So again, this is kind of pictorially what macro fouling looks like, debris fouling. Debris is pushed up onto the tube sheets and plugs those tubes so flow can't go through those tubes. Okay, so let's go back here to this plot here. So now, because we were able, by the way, the plant did not know this was occurring. It occurred in the winter time, okay? So when pressure is already low. So if your performance program is to just look at absolute pressure, in the winter time, if something were to happen, that pressure is low. It may not register on your radar as this being a problem. But with this equipment installed, we have a good relationship with the engineer there. He just sent us the data. He's like, well, why is this occurring? And we said, well, it looks like macro fouling, what's happened? And it turns out that they had a delivery of gravel to the plant, and the delivery vehicle got too close to the cooling towers, dumped a lot of the gravel into the basin of the cooling water towers, and all of that gravel got pushed to the condenser when the circulating water pumps came online. And so, this may not have been noticed without this instrumentation. There's no way to know, but I've seen it time and time again where a situation like this goes unnoticed, especially cooling water debris fouling. And so they had an opportunity in January, just 2 months later, to go in and clean it. And so they did. They went in, they got rid of the debris that was pushed into the water boxes. They took out tons of gravel. And so then they came back up online after their New Year's outage. And you can see here the cooling water flow rate is at the design value of 156,000 gallons per minute. The east and west cooling water flow rates are very nice and steady. And we've returned to the unit's historically best cleanliness factor of 67%. Again, this unit has a lot more issues, but at least the cooling water issue was solved here. So the one thing that I want to point out here is that this problem, and I thought I had it in the slide, but in addition to this in addition to the excess back pressure that I talked about at the beginning of the slide, this was an additional 6 or 7 tenths excess back pressure at high load. I think 3 tenths at low load. This right here, if undetected, is a $500,000 problem per year. So if they had not detected this, this is a big problem. So that's the value of the problem that we found here. Okay, so that's the first case study. I'd like to continue on the case study with this same exact plant, a different time period. We have the same instrumentations installed, but we're solving another part of their problem. And so it's the same plant, same value that we're chasing is this excess back pressure, same configuration, different time period. And so at this point, this is actually this year, not 2015, but 2018. They had some high back pressure due to air leakage. The excess back pressure due to that air leakage was quantified to be about 0.2 of an inch. So if you plug that into the model here, we're looking at if they're running an excess pump, about over $10,000, probably $18,000 per month, all the way up to $40,000, depending on what the issue is. Again, this is just a reminder to keep in mind that you need to pay attention to the cost of running a pump and the cost of excess back pressure. That's the value of this problem. So anyway, this plant, just to revisit, has 2 revac probes. These are instruments measuring the multiple measurements in the vent lines. For those of you that don't have a revac, it's measuring pressure, temperature, flow rate, humidity in these lines, so we know exactly how much water vapor, exactly how much air is coming out of each of these lines, each out of the east path and the west path. So the west path and the east path vent lines. So we're monitoring air and leakage and vacuum pump capacity very well here. And so let's take a look at the data. And again, I'm going to ask you for your interpretations of this data. So when we arrived, this is the data that we saw. And so I'm going to walk through what the data is. This is the dashed data is from the revac on the east side. So the east side bundle. So we have red is the air in leakage value from that east side probe. Black is the total flow rate in cubic feet per minute of that east side probe. The mass ratio, which we really haven't talked about yet, you can kind of ignore for now, is down here in the teal, the light and dark teal. And then the west side probe has its air and leakage shown in dark red down here, and the west side probe has its total flow rate shown here in black. So we can see a difference. And so what you might expect to see in a well operating condition, you might expect to see that the pump's capacity is split equally between, because there's only one vacuum pump in this situation. There's one vacuum pump on a common line. It gets split. Let's go back to the diagram before. So there's one vacuum pump here. You might expect to see the same total flow rate coming from this line and this line, but that doesn't always happen, okay? And you might expect to see the air and leakage be the same from this line and that line, okay? That's maybe what you would normally expect to see, but we don't see that in this data, okay? So I'm asking for you to submit your guesses, educated guesses as to what's going on in this particular case. Now, we already know that the customer said there's high air and leakage, but what information can you glean from this plot? Not only is air and leakage high, but why is it imbalanced? What are your guesses as to why the flow rates are different in the two lines? Go ahead and answer that into the question box. Again, you might expect to see the air and leakage be equal on both the east and west path, and the total vacuum pump capacity to be the same on the east and west path. Yeah, so we've got an answer, and that's right. So with a 2 revac approach, you can kind of narrow your search for leaks. It looks like the leakage leaking into the condenser is closer to the east path tube bundle. So let's go back here. So we might have a leakage coming in the wall here, or maybe in the transition hood here, closer to this east path bundle. And so that air would go in, enter this bundle, and get evacuated out this pipe, and it would not travel all the way around the condenser and come out this pipe, okay? So there's air and leakage closer to this bundle and not this bundle. Another thing we can determine is that air and leakage is not up here. It's not around the expansion joint. It's not near the gland steam seals, because if air and leakage were to come in from up there, it would get entrained with the steam duty, and it would get split somewhat evenly between the two bundles. Okay, so with the two revac approach, you can see not only is air and leakage high, but we can also limit our search for where the leakage is coming in. And so we came on site with a helium leak detector, sprayed around, and we found that they had recently done some maintenance on an abandoned drain, and there was a steam sealed packing gland on this valve here originally. They replaced it with a valve stem that did not require a steam seal packing gland, but they didn't plug up the drain here. And so this drain goes around here, goes around to the other side of the condenser, and goes into the shell wall as one of the drains entering that wall. And so this was abandoned. There was a large leak coming in here. We found that with the helium leak detector. We were able to plug it. And so here's the data after we got that fixed. This is very busy, but let's just focus on one parameter, one color of data, and that is the red data. This the east I think that should say east, but anyway, there's two air and leakage values. The air and leakage value is solid red, and the air and leakage value that is dashed red. And so you can see here that once that drain was plugged, the air and leakage value bloop, plummets back down to a low value of 12 SCFM. The other side has 5 SCFM. They had some other leaks that were identified, some of the water box joint. There was a significant leak on their vacuum breaker. There was some other smaller leaks on some other valves. I don't remember which all ones were, but the big ones were on the water box and vacuum breaker, I believe. But so there's some remaining air and leakage, but they fixed the big one here, and now their air and leakage is low. So case studies 1 and 2, very simple. They're going to get a little bit, we're going to look at other troubleshooting techniques, but I wanted to keep it very simple, just looking at total flow rate and air and leakage really, and how one might go about using the data to locate leaks. That's what this purpose of this case study was for. And so this one system over the last 3 years was able to identify 4 different significant problems. The first one being the macro fouling, the debris fouling in 2015. There were other high air and leakage time periods in 2015, 16, and then I just went over the case study in 2018. So let's go on to the next case study. This is a plant in overseas. This is an 800 megawatt power station. The plant was fairly new, been 3 years in operation. They have ball cleaning system, large Nash 3004 pumps. They had some serious issues, many months, many consulting engineers concluding that the condenser target pressure was not being met. And so one of the areas that they needed help and wanted some expertise from us was air and leakage and pump capacity related, especially the re-evac tool, because it's really the one tool that'll give you a definitive answer on if air and leakage is causing a problem and if your vacuum pumps are pulling what they should be pulling when measuring it continuously online in situ. So we were asked to go overseas and perform some testing, so we drew up a nice test plan and installed some instrumentation there. So I'll go over that. So here's the value estimate. The value estimate is 2/10 at 800 megawatts, 2/10 at 500, their idle load. So we're looking at a $17,000 to $55,000 per month type problem. So that's the value of this problem. And so just to give you an idea of the configuration, now we installed some other measurements, but the ones that are important for this case study are 4 re-evac probes. We basically showed up on site with 4 re-evac probes, installed them while we were there, took them out when we left. And this is what the unit looks like. This is the two bundle arrangement. They've got two shells on this very large 800 megawatt unit. So there's a shell here. There's another shell here. And we put revacs on each one of their air offtakes to try and solve their problem for them. When we arrived, we had to move, that's what it was. So I'm not, let's just go with here. We moved the probe. They didn't believe the data when we first got there, so they said, let's move one of the probes. And I don't have the data right when we got there, but I'll show it to you. I'll show you why they didn't believe it. But anyway, we moved one of the probes to swapped one of the locations to the common line. So this revac probe went to the common line. The common line goes to their vacuum equipment. So now we have no revac in this offtake. We have one in this offtake. We have one in the common line, which is the sum of all four, and then one here and one there. So let's take a look at the data once we move this probe. And so this is why they didn't believe it. We saw air leakage over this bundle, coming out of this bundle at 40 SCFM. And almost no leakage at all coming from the three other lines, 1, 2, 4 SCFM here. The other reason they didn't believe it was really this reason right here. It's the total flow rate. The total flow rate measured, which is essentially the vacuum pump capacity, was 1,780 SCFM. Okay, so that's what the vacuum pump is pulling. That's the total flow rate. And so what they didn't believe is that the total flow rate from these other bundles could be so low. 140 CFM, 70 CFM, I mean almost nothing coming out of this bundle, 20 CFM. And all of the capacity coming from this bundle here, 1,558 CFM. So that's the reason they didn't believe it. Well, once we swapped the probe, everything continued to sum up, everything was in line, and started to explain the problem here. Just because you have a vacuum pump on the common line does not mean that that vacuum pump's capacity is going to be split evenly to all these bundles. And this is a very common occurrence, that when the air leakage is high to this bundle, the pressure tends to go higher here. And so if you just think of it as a hydraulic circuit, all these pipings that is a hydraulic circuit, I don't draw it out here, but if you do draw it out, you'll see that the hydraulic circuit will show you that the total flow will increase in this bundle and it will decrease in all of these bundles. If anybody wants me to go through that in more detail, I can. I didn't think it was important for this case study, but it's a very common occurrence that the total flow rate will be preferential to where the air leakage is coming from. So let's take a look at the data here. Sorry. Anyway, that's what we found. So the takeaway here is that there's air leakage somewhere probably on this wall. It's not from up high in this shell. It's probably on this wall coming in through one of the drains. And so they can limit their air leakage search to this wall and all of the systems attached to this condenser wall over here. Now, as part of the other testing that we did at this unit, we tested the effect of adding a vacuum pump and tested the capacity of the vacuum pumps. That's what one of the things we were charged to do, is make sure the vacuum pumps were performing adequately. And so let's take a look at the data, the time data here during a pump swap. So here we are, January 2016. Let's see here. So over here on the left, we have vacuum pump B operating. In here, in this region, we have both vacuum pumps A and B operating. And over here, we turned off vacuum pump B and operated vacuum pump A. And so what we're looking at here is the total flow rate, making sure that the total flow rates look adequate for each pump. So we would expect to see the CFMs from pump B only match or very closely match the flow rate from pump A only. They're close, it's not exact. It looks like pump A is working better. I'm going to go ahead and throw that answer out to you guys already. So vacuum A pulls more cubic feet per minute than vacuum pump B. It's not much. You can see here's the air and leakage during the vacuum pump swap. The air and leakage is pretty much flat. It's 40 SCFM with one pump, with two pumps, and with three pumps, and that's what you would expect to see. You know, this is air and leakage going into the condenser. Has nothing to do with how many vacuum pumps you're running, so it is essentially flat through all of this vacuum pump swap testing, 40 SCFM. What you do see is that we are able to reduce the condenser pressure by running two vacuum pumps. And so you may have this probably is very common for you all at your operating plants. When you suspect an air and leakage problem, the very first thing you do is try not to waste money. So turn on the vacuum pump. Turn on your backup vacuum pump. And so that's what this data shows here, is that if they turn on a second vacuum pump, these dark blue lines are their measured condenser pressure. So if they turn on two vacuum pumps, they can actually reduce their their condenser pressure here by about 1/10 of an inch, 1/10 to 2/10 of an inch here. So as part of your troubleshooting efforts, if you suspect high air and leakage, the very first thing you can do is turn on another vacuum pump and try and lower condenser pressure. Let's move on to the next case study. Here's another case study. This is a 210 megawatt combined cycle power station. They have a 130 megawatt steam turbine generator, so it's a combined cycle unit. It's a new plant, 15 years in operation. They have two Nash TC7 vacuum pumps, each 60 horsepower. They always run two pumps. So this is one of those plants that, you know, they just, that's their condition, is to always run a second pump, no matter if the air and leakage is low or high. But in this particular case, they had many months condenser target pressure not met. The excess back pressure was about 1/2 inch. And so let's take a look at the data here. 1/2 inch, the value proposition here is about 13,000 to 35,000 per month using that calculator. Here's the unit. It's a small combined cycle unit. The steam comes in from the side of the condenser. There's only one inlet water box, one outlet water box. Let's see. This is their vacuum line. So they have installed ball valves in the vacuum line. So we came on site with a rental Reovac, installed it in the line, got some measurements, measured the vacuum pump capacity. Let's take a look at the data. So here's the data when we arrived. Again, red is air in leakage. This is a different plot. This is a percent scale over here, and the maximum value for each line is shown up here. So this is 100% is 120 SCFM up here. So 60% of 120 is about 70 SCFM, 80 SCFM right here. So let's focus in on 3 lines here. I'm going to throw in another parameter. It is the most important parameter when looking at Reovac data, and that's this teal line, this water to air mass ratio. Okay. Now, I'm going to talk about it in a few slides why this is the case, but if this value is ever below 3, you have a problem with air and leakage or low vacuum pump capacity. It's the one number you can go to and know for certain if you have an air and leakage or vacuum pump problem. So if this value is below 3, you got an issue with one of those two things. So that you can, it's a very a nice parameter. So we'll talk about why that is in a couple of slides. But here's the air and leakage at 70 SCFM. They're running along. This is their volumetric flow rate at about 1500 CFM, which is a decent flow rate for their two small TC7 vacuum pumps. And so with this data, we can tell, number one, their vacuum pumps are pulling what they're supposed to be pulling. Their air and leakage is high. They did not have any methods for monitoring air and leakage. They had some pretty poor condition rotometers on their vacuum pumps. And so they didn't know if it was vacuum pump capacity related or air and leakage related. So immediately, right after you get the re-evacs in line, you can see immediately that pumps are working well, air and leakage is high, and they've got a problem here. So we conducted a helium survey here. I did want to talk about the water-to-air mass ratio now. So the water-to-air mass ratio, it is the most important parameter from the re-evac tool. Let's talk about what that. Let's figure out what that is. It's probably a new parameter for most of you. So here's a re-evac instrument. It's installed in the air offtake from the condenser. We talked about stagnant zones yesterday. We talked about airbound zones, and so let's think about the state of the gases right here at this air offtake. If you have low air in leakage, let's take the case of no air in leakage, okay? So there's no, it's absolute zero. What's coming out of this line is steam. It's water vapor only. And so this parameter that I say is the most important parameter is the water vapor to air mass ratio. So in the case of no air in leakage, the water vapor to air mass ratio is infinity. It's very, very high. Now that never is the case in a real world situation. There's always a little bit of air in leakage into a condenser. But a high water to air mass ratio means there is no stagnant zone. There is no air storage. There is no degradation of tube heat transfer coefficient in this area. And so a water to air mass ratio that is high is good. There's no excess back pressure due to low vacuum pump capacity or air in leakage. Now let's take the opposite, the extreme case where there's a huge air in leakage and there is air being stored around this stagnant zone. Well, then you do have air in leakage. You have less steam flow and more air flow. And so the water to air mass ratio is low in this case. And so what we have seen in hundreds of condensers is a relationship, a very clear relationship between the water to air mass ratio and the performance factor or the cleanliness factor of the unit. Okay, I make the argument that the water to air mass ratio is directly proportional to the size of this stagnant zone, to the number of tubes being shut off from condensation by air. Okay, and so let me show you what that looks like in every single condenser we've monitored. Okay, it looks just like this. So here's a plot of performance factor, your cleanliness factor or performance factor, your HEI cleanliness factor, versus the vent line water to air mass ratio. This relationship occurs in every condenser, every single one. So when your water to air mass ratio gets below a value of, sometimes it's 2, sometimes it's 3, sometimes it's 1 in some condensers, okay? But this relationship holds true to every condenser. When that water to air mass ratio goes low, the performance factor takes a dive. And so this value right here is directly proportional to the amount of air storage you have in your condenser. So let's talk about using the terminology that we went over yesterday. Our rule of thumb for all you re-evac users is that if the water to air mass ratio is less than 3, you've got an air and leakage problem. If it's greater than 3, go look somewhere else. It's fouling, it's air binding, it's it's low circulating water flow. It's one of those other issues. But if it's below 3, you can turn on a vacuum pump, or you can reduce air and leakage and reduce your back pressure. So let's talk about the terminology that we went over yesterday. So above 3, there's no stagnant zone. There's no bubble right at your air cooler. Below 3, you have a stagnant zone formation. Okay. And then you can see here, this is the trend line for this data that we have plotted, this trend line. This curve flattens out at about 80% cleanliness factor. This performance degradation right here is not due, if your data is up in here, it's due to scaling or fouling or one of those other issues. It's not due to air and leakage. So this plot is a very, very important plot. If you don't ever plot this data up, you don't have to. You know, you don't have to plot this data, but walk away from this session, walk away from this class, knowing that if the water to air mass ratio is below 3, it's an air and leakage related or vacuum pump related problem. So let's go back and take a look at the data. The water to air mass ratio value here on a scale of 10 is less than 1. It's less than 5 actually, or less than less than 1, less than 0.5 here during this high air and leakage period. We found the leak. I'll show you where the leak was, but we did find the leak. We repaired one leak and then repaired another leak. There were 2 leaks associated with this one leak. I'll show you where they were. But anyway, as we went along, we repaired the leaks. The total air and leakage came down. The water to air mass ratio goes up above 1. So it's better now, but they still can reduce air and leakage further to reduce their condenser pressure. And here in the blue line, you can see is their condenser pressure. It decreases as the air and leakage decreases. You can also see that we've plotted the cleanliness factor for the unit. That's shown here in green. The performance factor, the cleanliness factor is 40% here. And then after the air and leakage is fixed, it raises up to about 70%. So the problem that we found was there I am there. So this is the turbine exhaust. Here's the turbine annulus here. It goes into this exhaust connection here. And this particular unit again has an axial turbine. There is a bearing that's inside this casing, and there's that bearing. One side of the bearing is at atmospheric pressure, and typically this vent should be spitting out a little bit of warm air or steam, but it was actually pulling in a lot of air. And so that there was a problem with that, a leakage through that bearing. So that's where the air and leakage was. Now that bearing also has a drain at the bottom down below the condenser. And so air and leakage was coming in here and at the drain down at the ground level. And so we ended up bagging both of them to temporarily shut off the air and leakage until they could completely fix the problem. And so here is the pressure reduction that we were able to achieve by shutting off that air and leakage. Here's the excess condenser pressure that we calculated versus the steam turbine generator load. And you can see here is where we bagged both of those vents. So we reduced the back pressure, excess back pressure, from about 0.8 down to 0.2 of an inch. Okay, so I'm going to invite you guys to participate in this one now that we've covered a few of them. Yeah, what's
It's actually been about an hour.
Oh, okay. Let me finish this one because this is the same plant, identical unit. So let's finish up these. This is a case study at this identical unit at the same facility. Excess back pressure. Here's the value of the problem. You can take a look at that. Again, it's the same unit, same Revac probes. I'm sorry, it's a mirror of the same unit. And so here is the data. And so I'm going to ask you all to take a look at this data. What problem do you see? Is it a vacuum pump problem or is it an air and leakage problem? That's the first question. So we arrived on site here at this point. This is the data that we saw. is this a vacuum pump problem or is this an air and leakage problem? Looking for some responses. Go ahead and type your answers into the question box. We arrive on site and we can clearly see the water to air mass ratio is below 3. It's at 0.5. So we have a problem with one of them, either air and leakage or vacuum pump capacity. You know, the flow rate from that pump, if you recall, 1,400 pounds per hour was, or 1,400 cubic feet per minute was a good flow rate from those vacuum pumps. And so when we arrive, we can see that the vacuum pump is pulling about what we would expect. So, okay, I'm starting to see answers come in now. So you can see here, yeah, it's an air and leakage problem. The air and leakage is quite high here, 80 SCFM. Water to air mass ratio is low. They definitely have excess back pressure due to air and leakage. And so we went along here. We did find the air and leakage at this point. You can see it's kind of widely varying. I'll show you why that is, but there's an issue there. But anyway, right here is where we shut off the air and leakage. The air and leakage came down, the water to air mass ratio went up, and the back pressure came down here. So the problem here was the condensate drains tank. There's all of these drains that go into this tank down here. It's a high temperature tank. It takes a lot of abuse from thermal energy. And then this tank vents into the condenser. And so all of these drains come in. It's kind of abrupt. There can be an abrupt dump of load or water or steam into this tank, and then it gets vented. It's constantly vented out to the condenser. There is a controllable steam valve into here that they can control the steam pressure into to try and purge the system out. And that's the reason for, there was a leak in one of these valves. So let's take a look at where the leak was. Again, this was found with the helium leak survey. So here is how you can see that. Whoops. So let's turn that down. Anyway, so you can see that as the air is flowing into this flange connection here, it pulled in a feather. There's a large amount of air entering this area, and you can see here that these bolts, these nuts on these bolts of this flange were not tightened, and so this flange was leaking quite a bit, So after we left, the flange was eventually tightened. The air and leakage was kind of all over the place because the pressure of that tank varies so widely depending on if something's draining to it or if something's not draining to it. And so that changes the pressure of the tank. And so since it's just essentially an orifice across the tank, it pulls in more or less air depending on what's draining into that tank. So the loose flange time period, the air and leakage is kind of all over the place. It's high and it's low, it's high and it's low, depending on what the pressure of that tank is. Well, once the flange was tightened, here you can see the y-axis air and leakage. Once the flange is tightened, the air and leakage is at a nice low value here. Not as low as it should be, but below 30 SCFM, much lower than the 80 to 100 SCFM that we saw when we arrived. One last case study here. We'll go quickly through it. Again, same facility, same setup. I'm not going to ask here. You guys know 1400 CFM is a good flow rate. The air and leakage was high here. We found a gasket that had a hole in it. We bagged it, and there was another. This was a spray, hood spray connection. that was broken here. You can see at this connection, it was broken right there. It's hairline fracture. Sometimes you could see it, sometimes you couldn't. But right there was one of the major leaks there. And so you can see here, when we arrived, this is where we bagged that gasket, and this is where we temporarily shut off the leakage to that hood spray. You can see the air and leakage takes a dive. You can see the water to air mass ratio goes from about a value of 1 all the way to 4.5. So this unit was fixed to a value of a water to air mass ratio above 3. So now they have no more excess back pressure due to air and leakage or vacuum pump capacity. A nice fix for them for this unit. So with that, let's take a break, and we'll come back, and we're going to take a different tack on some of these case studies. I'm going to put a little bit more formulation to it, give you some flow charts to follow, and be asking for a lot more participation in the coming case studies.
Okay, Tim, how long did you want? 5 minutes or 10 minutes?
Yeah, 5 minutes, please.
5 minutes. Okay, we'll meet back here then at about 12 minutes after the hour. All right, welcome back, everyone. We'll go ahead and get started with the second half of today's session.
Okay, thanks, Kathy. So let's start off. This is a new flow chart, and it kind of summarizes what we've just talked about. Yesterday, I showed very vivid examples of how air is stored in the condenser. I showed those performance profiles of tube bundle arrangements when we increased air and leakage, and you were able to see the blue region grow out of the air cooler section as air and leakage went up. And now I've linked that to measurements that can actually be made with the REEVAC tool, the water to air mass ratio. And I've stated that it's the most important parameter because that water to air mass ratio is proportional to the number of tubes being shut off from condensation. It's directly proportional to the performance of your condenser as related to air and leakage or vacuum pump problems. And so when you go to troubleshoot and if you have a REEVAC, the very first parameter you should go to is the water to air mass ratio. That will tell you immediately if there is an issue. And so this flow chart summarizes what we've just talked about. And so for the next couple case studies, take a look at this flow chart. I just want you to focus on 2 diamonds. You can look at this in more detail later on after the class. This is a whole troubleshooting effort for looking at air and leakage or vacuum pump problems. But I want you to use these 2 diamonds on the next couple case studies to figure out what the problem is. Number 1, is the water to air mass ratio less than 3? If yes, then you've got a problem. If no, you've got no air and leakage related problem, okay? The next thing is if it's yes, if it's less than 3, is the cubic feet per minute, the ACFM, actual cubic feet per minute, is it as expected? You know, is it in the 1,000 or 1,500 CFM? That's where most vacuum pumps are kind of rated, and it changes from time to time. But for my case studies, if you're over 1,200 ACFM, you're good. If you're less than that, you probably got a problem. We can help you figure that out if you've got your vacuum equipment manuals. But anyway, 1,200 ACFM is a good value. So these 2 diamonds, as we go through the case study, is water to air mass ratio less than 3? If yes, what is the CFM to determine if it's an air and leakage problem or a vacuum pump problem? Hopefully that's very clear. And if it's not now, it would be in hopefully 3 slides. So let's go through the next case study. This owner has 2 Nash AT1004s, and in this data, he has swapped the pumps. He has gone from pump 62 to pump 61, okay? And so what I'm asking you to do is just focus on those those 2 diamond questions. And I'm asking you to go ahead and submit your answers into the question box. Number 1, you know, what is the mass ratio less than 3, yes or no? Okay, got an answer, good, yep. It's less than 3 here, right? It's less than 3 for pump 62. Yeah, there we go. Okay, so somebody's hit the nail on the head right there. So pump 62 is not good. Pump 61 is good. So how did he come to that conclusion? Water to air mass ratio is low on pump 62. Water to air mass ratio is high on pump 61. Okay, what's the ACFM? The ACFM is only 500 ACFM for pump 62. That's too low. Pump 61 has about 2,000 CFM. That's good. Okay. And what was the pressure? The pressure that they recovered just by swapping from pump 62 to pump 61 was about 0.2 of an inch. Okay, good. So pump 62 is performing poorly. Yes, exactly. Okay, so we can go through all of that here. And the conclusion from this particular customer is we've been trying to convince the maintenance supervisor that the pump wasn't working well, and now they have proof. Okay. Okay, this is a very, very useful plot. So this one of the nuggets that I want you to walk away with is you can very quickly assess the performance of your pumps using the RIVAC measurements. Here on this plot is the y-axis of ACFM. Let me get my laser pointer out here. ACFM, and on the x-axis is pressure. You should find these curves right in your vacuum pump manual. You can just take the measurements straight from the RIVAC, plot CFM versus pressure, and you get these pump curves. Now this looks kind of like a mess, but there's a reason for it. Okay, you see this blue curve, a green curve, a yellow curve, and a red curve here. This is all data from that case study we just talked about. Okay, there's pump 62 here and pump 61. This is pump 62, I believe. And the color ranges, you can see here, the color on the data is the time of year. Why would I put the time of year on this plot? Well, that's related to, we didn't have the measurement, but that's related to the seal water temperature being delivered to the cooling water on your vacuum pumps. Okay, so the seal water temperature is very important for liquid ring vacuum pumps. The seal water temperature acts as almost like a small condenser on your vacuum pumps, and so keeping that cold is really important. It determines the vapor pressure in the pump cavity. If it's too warm, you won't pump anything. That's a separate topic that I'm not going to talk about today, but keeping that seal water temperature low affects the capacity. So you can plot this data up and monitor it over time, and you'll get your pump curves. And you can tell if your pump is performing as it should be over many different times of the year, and compare it to manufacturer specifications. A very, very useful plot for monitoring your vacuum pump performance is CFM versus pressure. There's the poorly operating pump 62. And there's your working pump 61. And there's your different curves for the different temperature of cooling water or seal water, essentially. Here again, for that same bit of data, is the performance factor for that unit versus water to air mass ratio. There's your curve. So for this particular unit, yeah, I would recommend below 3, keeping water to air mass ratio above 3. Okay. Now this is an no, that's a different issue. This is an Ingersoll-Rand unit, has its own performance issues, but anyway. Yeah, that's what that refers to, is its performance degradation due to its design. And so there's just a reiteration of stagnant zone versus no stagnant zone, is that water to air mass ratio of 3. So here's a table. I have not talked about validating data, and it's one of the nuggets that you should walk away from this session is validating all your data. We have not talked about validating re-evac data, but it is an important part of the process. And so I want to go through a case study where we validate the measurements from the re-evac tool. They can help you solve problems. So this table, anytime you suspect a problem with your condenser and it's air and leakage related, or the re-evac seems to indicate it, go through these steps. Validate the data first. Okay. So number one, the re-evac pressure should be slightly less than the condenser pressure. It's downstream of the condenser. It should be slightly less, about 1/10 to 5/10 of an inch. The temperature, the re-evac temperature, the off-gas temperature should be greater than this cooling water inlet, but it needs to be less than the saturation temperature or the hot well temperature of the condenser. Okay, so that's how you can tell if the re-evac temperature is right and if your other temperatures are right going into your assessment. The mass flow. The mass flow is related to the flow rate of that's in the vent line. It should be less than 1,000 pounds per hour, or it's about 225 to 600 per pump. The relative humidity or relative saturation should be below 100 and varying. These are all validation parameters. And so you want to go through this. You want to use these conditions, and you want to answer yes, 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 or no, yes, yes on those. So we're going to use this table on the next case study. So here's the setup for this one. This is a unit, a condenser with 2 offtakes. They have 1 re-evac in the common, but downstream of the re-evac is 3 vacuum pumps: pump A, pump B, and pump C. Okay. So let's take a look at the data from the re-evac as this particular customer turns on the different pumps. So let's look at this data. So if you have your data slide, you can pull that out, and then you can also look at the validation parameters from the handouts, the table. So here's pump B, pump C, pump A. So I'd like you to use that troubleshooting flow chart. What's the first question we should ask? It's, is the water to air mass ratio less than 3? It's in teal. Yep, it's less than 3. Yep, right. Okay, and so is the vacuum pump capacity up where it should be? I've stated that most pumps should be operating about 1,200 to 1,500 ACFM, especially these Nashes. No, they're not. That's right. So we got an answer. So are all 3 of these pumps not working right? Yeah, they're all not working up to specification. That's essentially what this is boiling down to. Look at the air and leakage. The air and leakage is at about 17 SCFM. Not a really low value, but certainly not a high value, and certainly not one that would put your water to air mass ratio down at 0.5. I mean, that's a problem right there. They got pretty low back pressure. They're operating in the wintertime, but this is really low water to air mass ratio. They could reduce that pressure further. If they wanted to reduce condenser pressure, if there was a value to doing it, what should they do? They should operate all 3 pumps. But let's go through the validation of this data. Validation. The pressure, let's move to this slide here. The pressure should be, the re-evac pressure should be less than the condenser pressure. So go ahead and take a look at the data slide and see if the re-evac pressure is less than the condenser pressure. You could see it there in blue. There's the plant pressure, there's the re-evac pressure. Yeah, it's less. So temperature is the re-evac temperature between the cooling water inlet and the hot well. Go ahead and answer that. I've got an answer, yes, yes it is. Is the mass flow less than 1,000 pounds per hour? Is it between 225 and 600? And I got an answer to that. So we call that a blue yes. It's less than 1,000, but it's quite low. So there's a problem there. And then the relative humidity, yes. So now we'll handle a case study where I think we went through this. I'm going to blaze through some of these because we're kind of short on time. Anyway, all three of these are operating low. They could reduce condenser pressure by running all three. If they don't want to, they should be looking at maintenance. If all three are low, I would recommend looking at the heat exchangers. If all three of them are low, the heat exchangers have not been maintained, or maybe the seal water overflow has not been maintained. They're running dry. One of those two issues is probably is most likely the problem. Something that's affecting all of them. So that would be an issue. Okay, so we've handled all this. You can look at this stuff after the presentation. Let's see. This customer ended up reducing air and leakage. Okay, so we're gonna go on to the next case study. Okay, so this case study, there will be a problem with validating the data, so I would like you to find it. Here's the layout of this particular condenser. Here's a shell. They have a reevac, 3 reevacs, probe 1, probe 2, probe 3. And so I'll need you to take a look at your data slide and pull that out, hopefully in a separate graph. But here's, there's 3 data slides. There's AO3D, AO3E, and AO3F. These are the slides you should be looking at. And so on these slides, this is the common line. This is the 3rd probe. You'll see the plant back pressure. You'll see the reevac pressure. You'll see the circ water outlet temperature, the hot well, the inlet temperature, the reevac temperature. You'll see all of those on these plots. And so I need to fill out this table. So take a look at AO3, D, E, and F, and let's answer these data validation questions. So is the reevac pressure less than the condenser pressure? No, I got answers. Yeah, right. So good. So no, it's not. It's not for the first one. The temperature looks good. I'm going to blaze through since we already found the problem. The mass flow is a little bit low. Relative saturation is low, is less than 100 and varying. As somebody already answered, B, AO3E. It's also no. I've got answers coming in, right? No, that's right. And then all of these are yeses, right? How about the common line? Is the reevac condenser reevac pressure less than the condenser pressure? That would be AO3F. Yeah, okay, so we got answers coming in. No, right. Wow, 3 independent instruments all recording a pressure that is lower, or that is not lower than the condenser pressure. That's a bit odd. So let's put this on a plot. So here's the probe pressures: 1.9 inch from probe 2, 1.9 inch from probe 3, 1.9 inch from probe 1. So all of them in agreement, all in the same line. That's exactly what we would expect to see. But why is it higher than the condenser pressure? Okay. Well, we also have on those plots the condenser hot well temperature, and that hot well has a temperature where its saturation pressure is about 1.8 inches. Okay. Now the hot well temperature is not equal to the condenser pressure. It's not equal to it. It should be right at. If there's subcooling, then it can be lower. But boy, why is the condenser pressure being measured lower than the hot well saturation pressure? That's impossible. That is an impossibility. Can't happen on this earth. So what that tells us is that there is a problem with this plant's measured condenser pressure. We've got 4 independent measurements all telling us that this pressure condenser measurement that they're using to monitor condenser pressure is no good. And so that can be the value of validating your data, using the ReVac to validate your data. So which sensor is in error? We went through all of this. Plant pressure sensor is in error. Okay, they do have a leak. If you take a look at that data, you can see that they did have an error in leakage. Let's go to the common line real quick. Right here. So it looks like they did have an error in leakage. Wow, look at that. It went from about 5 SCFM all the way up to 60 something. So let's figure out why that occurred. So where's the leak? What did the A side do? Oh yeah, so let's practice some of this. What did the A side probe do? Did the air and leakage go up on the A side? So that would be A03D. Did the air and leakage go up on the A side? Yep, sure did. Good. Did the air and leakage go up on the B side? That would be A03E. Yep, good. And the common side also went up. Looks like you guys are catching on. So what would you expect from a leak on A side or B side only? You would expect it to be on those sides, right? Well, they had a leakage that went increased on both the A side and the B side. And so the inference there is that the air and leakage event, the air and leakage source is, that's right, somebody already answered. It's up near the turbine, right? It's expansion joint. It's gland steam seal. It's up there near up the top where the air can get entrained with the steam, split evenly between the two bundles and come out. And so that's exactly where they focus their efforts. This plant likes to use the ReVacs to narrow their search for leaks, and they looked through the data historian. They found a seal steam pressure drop. So the steam seal regulator failed. There's the steam seal pressure in blue. It dropped right as the air and leakage went up. Okay. And then here they increased the steam seal pressure, boom, right there. And then the air and leakage, boop, went right back down. So excellent. Great. This very quick responses. Thank you. That's great. Okay, so I want to, that kind of concludes some of the data case studies. I do have some more case studies, but they're of a different nature. I wanted to summarize the important points of the case studies when we went over, okay? Number one, hardware needs. You need to validate your instruments. We did some data validation yesterday. We did some data validation more today. You can do that. You can have a basic test grade monitoring package. And then with that information, you need performance models. So you need to be able to calculate a performance factor or a target pressure. And then at least one of our attendees is working on developing those models. So once those are in place, what are your go-to indicators for troubleshooting the condenser? You know, there's only so many things that can go wrong with the condenser. The go-to indicators are, number one, your water to air mass ratio from your ReVac equipment. If it's less than 3, boom, you know what the problem is going to be. If it's greater than 3, you got to look elsewhere. Okay, is the cooling water flow at design? That's a very easy one to do. If you have a measurement with the differential pressure meters, like I've suggested, you can get it that way. You could also do a cooling water balance using the formula. If you've got a value for duty, you've got your inlet temperature, your outlet temperature, look at your calculated cooling water flow rate. So that's another way you can check off one of the problems. And if it's not one of those, or if this one doesn't indicate macrofouling, then it's probably scaling or something like that. So by process of elimination, very quickly you can cover all of the things that can go wrong with the condenser. This is number one. That's number two. And then by process of elimination, you probably have a scaling issue or an air binding issue. Okay, so some useful analysis, troubleshooting, and reporting. So if you're going to report this to your peers or your supervisors, okay, You want to calculate values to quickly value the problem. We went through that with that Excel spreadsheet, valuing the problem, trying to figure out what's this worth, what's the dollar value. You may have a different method. You may want to quantify it in heat rate. We've shown you methods for that. But so that's a nugget. Value the problem so that you can communicate that to another person. We've given you some options. The performance factor versus water to air mass ratio, a very useful, very, very useful plot to have at your disposal. You only need one event to create that, and then you'll forever have it. You'll forever know how much heat transfer is being lost just by measuring this water to air mass ratio. Your pump comparison plots, another very useful analysis technique. If you plot your pump plots, the CFM versus pressure, plot those out. Put them in a binder. Then forever you always have a baseline for your pump performance. You'll always know what CFM you should be measuring at any given time. So making those CFM versus pressure plots. That's this one. Making a pump comparison plot. So if you have 2 or 3 vacuum pumps or vacuum pumps and steam jet ejectors, you can swap them in and out and do your comparisons that way. That's another useful analysis technique right there. Something that's not on this list is swapping the probes. We didn't really go over that, but there's some case studies that we have that show the value of, if you don't believe a measurement coming from the reevac tool, or if you want to narrow down the location of a leak, take that reevac probe out of the common line, move it to an individual line, or swap the probes. Move one from A to B side to A side to validate your numbers. That's another useful technique. And then the other thing is multi-axis plots. If you ever need help there, we can help you with that. But that's a really useful way to convey the information to another person and report it. So one of the last things that I'm going to talk about today is condenser improvement projects, condenser upgrading projects. So I've talked a lot about the Westinghouse condenser being a poor design. There are some Ingersoll Rand condensers that are very poor designs. I've shown you the thermal performance profiles and shown you where there can be dead zones that are always there. No matter what you do, you can reduce air and leakage to very low levels, and those areas will still be bound up. I've shown how fouling can affect performance. And so if you're ever looking to improve the performance of the condenser and your troubleshooting efforts are kind of reached a dead end, there's a process to go through to figure out if a condenser performance improvement project can be justifiable. And so it starts off, it's a staged approach. Step 1 is a basic performance evaluation. It's using all of the techniques that we just went through yesterday to validate your measurements, get a baseline performance measurement, and make recommendations for improving instrumentation. So then if it's justifiable, improving instrumentation, instrumenting areas where there's value would be a step 2. Step 3 would be to go do another advanced performance evaluation using test grade instruments. There's all kinds of options here, whether you're doing the tube sheet instrumentation that I showed yesterday or not. It could be as simple as just putting in the system that Spurlock can put in place. That can be an advanced performance evaluation. And then step 4 is using that better data, using that advanced performance evaluation to make engineering decisions, make a design change. I don't know, implement a reverse flushing mechanism for your plant. Maybe macro fouling is a problem that really needs to be addressed. You've now quantified the value, and so going through in engineering a reverse flushing system would be of value, or going through and addressing air binding in the condenser. And so I want to go through some the process here of a case study where we've done that. We've gone through all 4 of these steps. Now I'm going to skip some slides here. I've more clearly defined what step 1 is, step 2, step 3, and step 4. You can go through and read all that stuff, but it's detail that's really not useful at this point. So I want to get right to the case study. This is a plant. We went through step 1, 2, and 3. We were able to identify an air binding problem in this condenser and justify stage 4. I'm going to show you the results from the phase 3 effort. Try and give you the reason for justifying this upgrade to this condenser. But this is a picture of us during stage 4. We've designed a change to the condenser. We've shipped all these parts, and during an outage, we installed a condenser retrofit. So here is a timeline. You can kind of look through this on your own, but this is a typical timeline. It's about a year to 2-year timeline to go from phase 1 to phase 4 if you're looking for a condenser upgrade project. There are some economically strong drivers for an upgrade project. Number 1 is if you're looking to increase the steam duty to the condenser. That would be an optimal time to ensure that the condenser is not going to be a bottleneck. If you have seasonal or permanent heat input limited conditions, so you've been at the plant and summer after summer after summer, you can't meet demand, your heat input limit, you put as much heat into the boiler, fuel into the boiler, and you still can't meet your electrical generation targets, that would be a particularly strong driver for an upgrade project. I've talked about the variable frequency drive cooling water pumps. Those are kind of rare, but if you do have them, there's a strong driver to improve the condenser. And if you have cooling towers, generally they will provide higher inlet temperatures, and so at higher inlet temperatures, you have very strong drivers for going forward with a condenser retrofit project. So here's the case study. This is a unit. This is an Ingersoll Rand unit. Here's a diagram of the unit. The cooling water comes in. This low pressure shell turns around, exits this high pressure shell. So this one operates at a higher pressure than this one. They have an Ingersoll Rand design. I'll show you what that 2-bundle arrangement looks like in a slide or two. They were going through a retubing. They keep their tubes extremely clean. They have a ball cleaning system. They have Admiralty brass tubes. They were going to retube with Admiralty brass. The wall thinning on the tubes was the driver for the retubing effort. They didn't have too many plug tubes. I think it was around 8%, which was their limit for retubing the unit. But the tubes were kept immaculately cleaned because of the ball cleaning system and their cooling tower maintenance. Very clean system. But anyway, they were going through retubing. During the work, they were also going to upgrade the turbine. Before this outage, about a year or two before the outage, we installed water box instrumentation and measured the performance profiles before the retrofit. We theorized what was causing the low performance before all of this was done. But anyway, I'll show you exactly where the performance degradation was. Here's the instrumentation system that we put in place. Main electronics, that's the brain of the unit. There's water box instruments on all these water boxes. There's pressure and temperature, inlet temperatures, outlet temperatures, re-evac equipment, all the equipment that we've talked about in the past couple days. But I do want to show you the results from the tube sheet instrumentation, and this will really highlight, really show in vivid clarity what the problem was with this unit, and I'll tell you about that. So here's their Ingersoll Rand bundle, tube bundle arrangement. On the left side image is the pre-retrofit clean tube performance profile. On the right side is the post-retrofit clean tube performance profile. And just to remind you all, this is not CFD. These are temperature measurements being made on the outlet tube sheet, measuring the temperature rise at many, many points on this tube bundle, measuring the temperature rise. And then we use that temperature rise to calculate the performance of those tubes. and then we colorize that performance on this scale. So you can see here, often I get questions, by the way, please ask questions. Often I get questions about this outer edge being above 100%. How can that be possible? Well, we talked about that yesterday. HEI is a conservative estimate of single tube heat transfer values. The ASME method is a much better representation, and it produces heat transfer values about 20% higher than HEI. Out here you have very high velocities, no condensate loading, and so you get much higher heat transfer coefficient values on the periphery of just about any bundle. And they approach about 120%, very near the ASME values. But as you get inside the bundle, the velocity decreases, you get condensate loading, you do get reduced heat transfer that more closely matches the HEI values. Anyway, this scale is the HEI performance value. And as I mentioned yesterday, I like to call your attention to the yellow values. The yellow values is about a 75% heat transfer value when compared to the HEI model values, and that gives you a nice boundary bubble to put around the air bubble in the condenser. And this is the way this Ingersoll Rand has always operated since the day it was installed. The reason for it is that they only shrouded the one bay in the unit. They didn't shroud all the bays, so it allowed the air to build up in all of the bays except the first bay. It's a catastrophic design oversight for this condenser, but it was part of our effort to implement a strategy during the REAP tube to correct that air cooler section. And so after the retrofit, we installed a proper air cooler, went through a whole design effort and approvals, and made the design. We're there to oversee the installation of the parts pieces to make sure that we vented out this bundle much more effectively, and you can see the results in the performance profile post retrofit. So we've gone from this bundle profile at an air in leakage of 18 SCFM into this bundle, well the whole unit really, and then over here this is a performance profile with even higher air in leakage, 27 SCFM into this bundle. Okay, and so you can see here that we've greatly reduced the stagnant zone and really the airbound zone in this unit. And so what I'd like to do is I have an animation that shows the pre-retrofit bundle while we did an air and leakage test. We increased the air and leakage from 18 all the way up to 100 some. And then in this bundle after the retrofit, we did the same test. We purposely introduced air and leakage, and you can see the marked difference between how this bundle manages the airflow. So let me go ahead and animate that. So here we go. Here goes the animation, and boom, there we go. So we're purposely introducing air and leakage in the left bundle pre-retrofit all the way up to 155 SCFM here. You can see that air bubble is now extended all the way out to the periphery, shutting off more than half of the tubes in this bundle. Terrible, terrible management of air in this condenser. And then over here in the post retrofit, there almost is no blue areas in this bundle. Almost all the tubes are above 60%, as opposed to here, they're all shut down. And this is with 100 SCFM into this bundle. Okay, so not by implementing a retrofit, not only have we reduced the air binding by better managing the steam flow, the airflow, but now this unit is much more immune to air and leakage, much more immune. So let's take a look at some of those results. So for a 15 to 65 SCFM pre-retrofit, the pressure in the condenser increased 0.8 of an inch, 0.8. So from 4.5 inches with the air binding in it, it went up 0.8 of an inch. With all of this air storage, the condensate dissolved gases went up 12 ppb with that SCFM increase. But post retrofit, look at these results. So post retrofit, going from 38 SCFM to 100 SCFM, the condenser pressure only increased 0.2 of an inch from a baseline of 3.6 inches. And the condensate dissolved oxygen only went up 2 ppb. So much more immune to air and leakage from a condenser pressure standpoint and also a dissolved oxygen standpoint. So let me throw more data at you. I'm going to show you the pressure, condenser pressure in this unit versus cooling water inlet temperature for the entire year of 2006. As a reminder, this unit has two different pressure shells. There's the LP shell colored in blue. There's the HP shell colored in red. And so there's the HP shell operating at 5/10 at 80 degrees inlet and 3/10 at LP shell. And this is all of the data for 2006 at greater than 560 megawatts. Now we did the retrofit in 2010. So let's take a look at 2007 data. Here's 2007 data. There's the pressure in the HP shell, pressure in the LP shell, kind of right on top of one another. I faded into the background the 2006 data. So then we advanced to 2008. Here's 2008. So again, this is just a history of poor performance. Here's 2009. They had a problem with their vacuum pump. One of their vacuum pumps failed, and so the LP shell produced a pressure that basically they lost isolation, but don't worry about that. In 2010, they fixed the vacuum pump problem. Here's still before the retrofit. So I just showed 5 years prior to the retrofit of data, pressure versus inlet temperature, clean operating data. And then we installed the condenser retrofit. Look at this. So we installed a much more effective air cooler section, and look at the pressure reduction. HP shell dropped an inch of back pressure in the HP, 6/10 in the LP. Okay. Keep in mind this design wasn't good to begin with. That's where the opportunity came from. But an inch in the HP, 6/10 in the LP. A really nice benefit here. So the benefits summed out to be about almost an 80 BTU per kilowatt hour reduction, permanent reduction in heat rate at 83 degrees, or an extra 6 megawatts, depending on how they operate in the summer, an extra 6 megawatts. So on a 600 megawatt unit. And I've already kind of talked about some of the air-in leakage immunity data. It's summarized here for you, pre-retrofit and post-retrofit. And here on the data, there's the excess back pressure, the DO increases, and something I didn't talk about was the cation conductivity from dissolved CO2. That also decreased, and much more immune condenser. And so that's the last slide that I have for you. I've walked you through fundamentals of monitoring to the condenser, troubleshooting your instruments that you have in your plant. I've talked about how to use the re-evac tool, how to monitor cooling water flow rate, and if you have a condenser that has been just a headache from the beginning, historically having low cleanliness factors, I've walked you through a process that you can use to find out if there's a project worth doing an upgrade on the condenser. And so I know it was very rushed there at the end. I want to thank you for sticking with me through it all. If there are any questions at all, I'd be happy to answer them now, and thank you for your attendance.
Okay, thanks, Tim. I'll go ahead and do some final housekeeping items here while we wait for questions to come in. Again, we want to thank you for attending today's webinar, and we did record today's session just like yesterday, so you will be getting a link to that either later today or tomorrow morning that you'll have access to for 30 days. You will also be getting a survey popping up in your email with a few questions, and if you have questions after the session and want to post them on that survey will be going to Dr. Harpster, so he will be able to see those questions and get back to you. Looks like we have some people signing off and no questions coming in. So with that, I'd like to thank Dr. Tim Harpster and Jason Reynolds for this excellent performance. And for the future, watch energytech.com for upcoming webinars. We do have some more coming up in the fall, so watch your email and watch our website for more things coming in.